Hello guys, today we are going to discuss about yesterday's, I think we have already discussed, about the diagonalization, and today now we will discuss the next part, that how the diagonalization actually works and how do we go for the, which matrices are not diagonalizable. So that example today we will take up. So let me take the matrix. Say let matrix A is equal to 2, 4, 3, minus 4, minus 6, minus 3, 3, 3, 1. And now we will see whether this particular matrix is diagonalizable or not. So that's the question. So to understand, as we know that the first step is to find the step 1, to find the eigenvalues of the matrix A. So for that, we know that the characteristic equation will be determinant of A minus lambda I equal to 0. Now this implies determinant of, we will take the determinant, that is 2 minus lambda, 4, 3, minus 4, minus 6 minus lambda, minus 3, and 3, 3, 1 minus lambda, which is equal to 0. Now we need to solve this determinant because it is a 3 cross 3 determinant, so it is easy to solve the determinant. Now what we do is, we will take 2 minus lambda here. This has to be multiplied with minus 6 minus lambda into 1 minus lambda, so plus 9, minus 4 into 1 minus lambda, so plus 9, so plus 3 into minus 12, minus 3 into minus 6 minus lambda, which is equal to 0. Now what we do is, so now 2 minus lambda into, can just simplify, minus 6 plus 6 lambda minus lambda plus lambda square plus 9. So minus 4 into minus 4 plus 4 lambda plus 9. So plus 3 into minus 12. This is plus 18 plus 3 lambda equal to 0. Now simplify further. It is 2 minus lambda. Here it is lambda square plus 5 lambda plus 3 minus 4 into 4 lambda plus 5 plus 3 into 3 lambda plus 6, which is equal to 0. So we do further simplification. So you can multiply with 2. This is 2 lambda square plus 10 lambda plus 6 minus lambda cube minus 5 lambda square minus 3 lambda minus 16 lambda minus 20. So plus 9 lambda plus 18 equal to 0. Now minus lambda cube, you can see 10 lambda, lambda square, 2 lambda square we have here, minus 5 lambda square we have here. This is minus 3 lambda square, and then 10 lambda, here it is minus 19 lambda and plus 19 lambda. So we cancel. So we have 6 plus 18, that is 24 equal to 0. So here you can take the negative out. Let me see. 18, and here also we have minus 20. So this will be 24 minus 20 will be just 4. That is nothing but, if I take negative out, it is lambda cube plus 3 lambda square minus 4 equal to 0. So you have a cubic equation here. So by substituting, say lambda equal to 1, what I get here is 1 plus 3 is 4 minus 4, that is 0. That implies lambda equal to 1 will be one of the the root of this equation. So lambda minus 1 will become a root. So we can divide this lambda cube plus 3 lambda square minus 4 by lambda minus 1. So we get here lambda square This will become lambda cube. Minus 1 into lambda square will be minus lambda square. So changing the sign, we will get here 4 lambda square minus 4. So plus 4 lambda, that is 4 lambda square minus 4 lambda. To change the sign again, this will be 4 lambda minus 4. So plus 4, if I multiply it as 4 lambda minus 4, so we are getting here 0. So therefore, we have got the quadratic equation, that is lambda square plus 4 lambda plus 4, which is equal to 0. So this implies this is nothing but it's a perfect square. Lambda plus 2 the whole square is equal to 0. This will give us lambda equal to minus 2 with multiplicity 2. So therefore now we have got two eigenvalues, lambda is equal to 1 and lambda is equal to 2. So hence we have to find out the eigenbasis or the eigenvector, that is your step 2. So for lambda is equal to 1, if I consider, as we have discussed, it should be ax is equal to lambda x. This implies ax is equal to 1 into x, or ax minus x is equal to 0. This implies a minus 1 into I. So this is your a minus I, augmenting that with 0. So this is your matrix. So whatever the matrix we have in that, from the diagonal entries, we are supposed to subtract 1. So this is 2 minus 1, 4, 3, and then minus 4, minus 6, minus 1, and then this is minus 3. We have 3, 3, 1 minus 1. So augmenting this with 0, 0, 0. So this will give us, this is going to be 1, 4, 3, minus 4, minus 7, minus 3, 3, 3, 0. So this is, so now we can see that R2 changes to R2 plus 4 times of R1, and R3 changes to R3 minus 3 times of R1. So we have to remove these two. This will give us 1, 4, 3, minus 4 plus 4 is 0, minus 7 plus 16. So you have minus 7 plus 16, that will be 9. Then minus 3 plus 12 is again 9. Then you have here 3 minus 3, that is 0. 3 minus 12 will be minus 9. Then 0 minus 9. So this is 0. Okay. Now R2, R3 we can change. So this element to make 0. R3 plus R2. If I do, I'll get here 1, 4, 3. Because there is no change in the R1 and there is no change in the R2. This is 0, 0 and 0. So here you can observe carefully. We can still take this 9 out from the R2. Therefore R2 changes to 1 by 9 times of R2 if I do. This gives us 1, 4, 3, 0, 1, 1, 0, 0, 0, and then this is the augmentation. Here you can observe clearly with the help of, you can see here there is the pivot position. Here also there is a pivot position. There is no pivot position in x3. Therefore, x3 will be the free variable. If you write it as a solution, so x1 plus 4x3 minus, 4x2 minus 3x3 equal to 0. And here it is x2 plus x3 equal to 0. And x3 is free. So this gives us from x2, from this I'll get x2 will be equal to minus x3. So this x2 value we can substitute in the first equation. I'll get x1 will be equal to minus 4x2 plus 3x3, and x2 is minus x3 and x3 is x3 only. So therefore from this I can substitute x2. I'll get x1 as minus 4 into minus x3 plus 3x3, and x2 is minus x3 and x3 is free. So write a solution. You are getting x which is equal to x1, x2, x3. So x1 you can see minus into minus 4x3 plus 4x3, 3x3, it is 7x3, and x2 is minus x3 and x3 is x3. So if I take x3 out, it is 7 minus 1 1. So this 7 minus 1 1 is the corresponding eigenvector with respect to lambda is equal to 1. Okay, so sorry, you can see here x1 will be okay, x2 will be equal to minus x3. So yes, yes, you have got the v1 here. Okay, so now similarly we can find out the eigenvector with respect to lambda is equal to 2, lambda is equal to minus 2. So when you have lambda is equal to minus 2, the augmented matrix will be A plus 2i augmented with 0. So therefore you can just take the matrix, that is 2 plus 4, 4 3, minus 4, minus 6 plus 2 and minus 3. So 3, 3, 1 plus 2. This is augmenting with 0. So here we get 6, 4, 3, minus 4, minus 4, minus 3. So 3, 3 and 3. This we are augmenting here with 0. So here what we do is, this will be 2 plus 2, that is 4. Yeah. Now here you can see that we have got the matrix by changing the R2 changes to R2 plus R1, and we just take from R3 1 by 3 out. Okay, so let's see. This is 4, 4, 3. This is 0, 0 and 0. This is 1, 1, 1 and this is 0, 0, 0. Now what we do is we just interchange R1 and R3. This will be 1, 1, 1. This is first, yeah, R1 and R3 let us change, then I'll change this, so 0, 0, 0. Now we can interchange R2 and R3. So this is basically we get 1, 1, 1, 4, 4, 3 and 0, 0, 0. So this is the matrix we're getting. Now we want R2 changes to R2 minus 4 times of R1. This will be 1, 1, 1, 4, 4. Then this is 3 minus 4, that is minus 1. Okay, and here this is 0, 0, 0. And now clearly you can see here is a bound position and here is a bound position. So there is only one free variable, that is x2. So, but if you see lambda is equal to minus 2 has the multiplicity 2. So therefore we are supposed to get 2 vectors. But if you write a solution here, you are getting only one free vector. One eigenvector. That is equal to 0 here. And from here x3 is 0 and x2 is, wait, if you write a solution, it is x1 equal to minus x2 because x3 will be 0 and x2 is x2 and x3 is 0. So clearly if I take x2 out, it is minus 1, 1, 0. So this is your eigenvector. But we are supposed to get 3 eigenvectors. So there are no other eigenvalues. So there are no other eigenvalues. We have no other eigenvalues, and every eigenvector of A, every eigenvector of A is a multiple of either V1 or V2 because we have the two eigenvectors. So hence it is impossible. It is impossible to construct a basis for R3 because we have 3 rows. That implies it has to be the basis for R3 using the eigenvalue of A. Okay.
So therefore, by diagonalization theorem, it says that if it has the three different eigenvalues, I mean distinct eigenvalues, then only we can say that it is diagonalizable. Else it has to have a three distinct eigenvectors, but here we fail to have the three distinct eigenvectors. Therefore, by diagonalization theorem, A is not diagonalizable. A is not diagonalizable. So basically, we have seen the example where A is not diagonalizable. So we observe that we have got the eigenvalues which are, let's say, lambda is equal to 1, lambda is equal to -2 and -2. We have got three eigenvalues, okay, which are, of course, they are all not distinct. But yet in the previous example where it was diagonalizable, we have got three eigenvalues where, of course, it was not distinct, but we have got the three eigenvectors. So thus it was diagonalizable, and finally we check the condition for A is equal to PDP inverse. But in this case, we have got only two eigenvectors. Hence, we conclude that there are no further eigenvectors. Whatever the eigenvectors we have got, those all eigenvectors will be either the multiple of V1 or they are multiple of V2, which is not the new one. So therefore, we say that the given matrix A, so this matrix A is not diagonalizable. Okay, so this is how we conclude the diagonalization, whether the given matrix is diagonalizable or not, by checking the corresponding eigenvectors. So this is for the non-diagonalization, guys. So we'll discuss the next concept in the linear algebra shortly. Thank you. Take care.